Hello once again, and thank you again for joining our workshop on graph transformers and what every data scientist should know about them. I'm Kitty Ivanovska, Marketing Program Manager at Kumo, and I will be your host today. In today's workshop, you'll have the opportunity to learn from experts from Stanford, NVIDIA, and Kumo. Before we begin, I'd like to extend my gratitude to Vijay, postdoctoral scholar at Stanford University, Rishi, senior deep learning engineer for PyG and at NVIDIA, and Matthias, founding engineer at Kumo. Thank you for being part of this online workshop. During this session, you will learn more about the core concept behind graph transformers, real-world application, and how to train your own graph transformers-based AI models. Before we begin, please remember to use the Q&A section to ask any question throughout the session. At the end, we will dedicate time to answer the most relevant question in order they're received. And now I believe we are ready to start, and I'd like to invite Vijay to begin this workshop. Vijay, I hope that you are ready. You can share your presentation, and over to you.
Thanks a lot, Katie. Hello, everyone. Let me share my screen.
Great.
Okay. Hello, everyone. My name is Vijay, and I'm a postdoc at Stanford University. I'll be introducing graph transformers and go through the basic concepts and how things are motivated from generalizing transformers from sequences or text to graphs. So I'll go through a brief background on what transformers are, how their designs are motivated, and how can we see things from a graph perspective. So to introduce transformers are deep neural network architectures that operates on multi-sets of input tokens. The input tokens can come from different modalities such as text, images, and these days often in speech and graphs as well. At its core, there's a use of a multi-head attention mechanism and positional encodings which encode the underlying sequential structure of tokens. So what is a multi-head attention mechanism? It's a way how feature embeddings for different tokens are updated or generated. So if let's say we have a sentence, the feature embedding considers all other tokens feature embeddings, and in a sense, attention to every other word is considered. It's done in multi-headed fashion where there can be different attention heads to capture some dimensions of informations and concatenate them into one feature embedding. But if we see, the order of the words does not matter. The attention mechanism is invariant to the order of the input. So on the left and on the right, both mean the same because the multi-head attention mechanism doesn't know the order of the inputs. But words in sentences have a very natural ordering which we want to encode and let our transformers know. For that, we use positional encodings. So what we see is that transformers do not see a sequence directly, but rather a multi-set of tokens, which is on the example on the right. And the sequential order of the input tokens is injected through positional encodings. If we zoom in on this architecture, there's a positional encoding which is added to the inputs. So in a sense, the sequential structure information is actually offloaded to the tokens itself, and transformers get the information of the sequential structure through this mechanism. If we try to plot the positional encoding, it looks like the sinusoidal functions, and one example can be the vector. For example, this is different values of the 6 frequencies of the eigenvectors or the sinusoidal positional encoding that we can get. So each dimension, each word has this 6-dimensional positional encoding if, let's say, we consider 6 frequencies. So the summary of this brief introduction to transformers is they offer several advantages over traditional RNNs. For example, the self-attention allows capturing dependencies across all input tokens, as we saw in the examples. Because of no recurrent dependencies, it allows a great amount of parallelization and scalability, which we have seen in the recent few years of great impact of how transformers have made AI to be more powerful, and in results of we see a lot of LLM-based advances. And finally, the attention mechanism also allows interpretability. In the recent years, there has been some work investigating some mechanistic interpretability of how tokens interact or what are the implicit dependencies of in transformers. So this is a very brief refresher on transformers. When we move ahead next, I'll show how it relates to graphs. So graph neural networks in general are neural network architectures that learn features of nodes in a graph in an end-to-end manner without any manual feature engineering. And it does so by aggregating local neighbor features through the use of message passing. On the right, we have an example which shows that in order to build the feature representations of a node here, it looks at the computational graph or the tree rooted at the center node, and it takes in messages from its one-hop neighbors and uses them to aggregate and update the feature representations of the center node. If we try to compare and see transformers through this graph lens, we will find that attention mechanism can be constructed as message passing, which has been a very nice revelation right from the early works of graph attention networks. So on the left, we have text. On the right, we have graph. We'll see that in both of them, there's a message passing operation going on, where on the transformer, the message passing becomes an instantiation with self-attention. On the right graph, there are different message passing operations in multiple graph neural networks. When we look at the positional encoding, which is the second important mechanism in transformer through the graph lens, we find that positional encodings are functions of the sequential structure of the input. So if we have a sentence, and consider that the sentence is actually a line graph, because it's also a part of like the arbitrary graphs that can be possible. So actually any sentence can be constructed as a line graph. And if we try to reconstruct through a graph view of what positional encoding means in text transformer, we'll find that we can take the adjacency matrix of the line graph, get Laplacians of it, extract eigenvectors, and if we try to sort k non-trivial eigenvectors, we get final position encodings n times k, which is exactly, or which resembles similar to the positional encodings defined in the original transformer. So this means that the positional encodings in transformers for text are a special case of the position encoding that can be applied to arbitrary graphs. And this is a motivation that allows us to move ahead and introduce graph transformers, which are extension of the standard transformer architecture from sequences to relational and graph structure data. And why do we need it? Because graph transformers allow better node identifiability through different positional and structure encodings and attention across all or many nodes, potentially capturing broader structural context in graph structure data sets. I'll go through both of these things in detail. So the key generalization designs are when we try to generalize transformers to graphs. The first is we try to have the message passing aggregation by defining it with attention functions similar to transformers. And second, nodes are injected with Laplacian position encoding, which is defined by the graph structure. And it is a generalization of what we have in the text transformers. So the first attention mechanism, one of the very basic generalization is to bias the attention mechanism as a function of neighborhood connectivity. So if we want to build a feature representation for a node, the attention mechanism will consider only those nodes which are present in the local neighborhood for a central node. And rest others, the function resembles very similar to what we have in the original transformers. Second, nodes are injected with Laplacian eigenvectors as positional encoding, something that I referred to with the graph view of positional encoding in the text transformer. So what we do is we take the k smallest non-trivial eigenvectors. It can come from any arbitrary graph using the same method of getting the adjacency, compute with the Laplacian, get the eigenvectors, and take a case sorted non-trivial eigenvectors. If we try to do this, we get k-dimensional vectors for each of the nodes, and we can simply attach to the node tokens as similar to what we see in the text transformers. And a good property of this kind of encoding is if we interpret it as colors, we'll find that nearby nodes have similar features and distant nodes have dissimilar features, which also in principle is similar to what we look at, what we learn from the position encodings definition in general for text, for example. There's a lot of other options of designing position encodings, and I wanted to go a brief dive on this. Why it matters or why there are multiple designs of it is nodes in graphs do not have a canonical order such as we had in sentences, where the sentences can be constructed as line graph, or Alternatively, they can be ordered by positions, and we can get a trivial design of position encoding. It's not like that in graphs. So nodes do not have a canonical order. So we need a way to represent node positions in graph structure, and often different methods have different limitations. So what we need ideally is graph position encoding should be distance aware, unique, and generalizable. So these are some of the properties that is desired. And what it will bring to the table is that if we look at the example illustration at the bottom, on the left, we have two graphs without position encodings, and all of the nodes look the same. The colors represent, let's say, the node feature vectors. But if we try to use the graph structure information, get the positional encoding, and assign these vectors, the graph position can be the positional encoding vectors. If we assign this to the nodes, it will help disambiguate nodes because nodes at similar positions and dissimilar positions get different and similar colors. So for this such example, if we don't have positional encoding, it will be hard for disambiguating this example pair of graph. But if we have it, we'll get a very easy way to capture the structure in order to disambiguate this kind of node. So this is an example illustration. There are the Lipschitz eigenvectors is one approach, but there are also other approaches such as those based on random walks, which is basically a way to encode the probability of random walk for a node visiting to itself in for a number of k steps and assign these values as a vector for each of the node. When we look at what information it brings the fact that each node can get a unique vector as long as its k-hop neighborhood is unique. And if we look at the illustration on the right, we see that this node and this node have the same color because if we look deeply into this diagram or into this graph, these two nodes have the exact same k-hop neighborhood for all values of k that can be considered. So overall, position encodings are a function of graph adjacency matrix, and the goal is to encode meaningful local and higher order structure information as node feature vectors or node positions. The next aspect about graph transformers is the coverage of attention. As I mentioned in the first generalization, we can bias it through a local attention mechanism, which is the neighborhood connectivity information. But while this local attention to neighbors is very useful, it provides a very rich inductive bias to the architecture. It may not provide broader structural context in many cases. For example, there can be some tasks that benefit from aggregating messages from distant nodes. Consider that this is a graph and there's a distant node at a very maybe 20 hops or 15 hops apart. It cannot be directly aggregated. If we were to apply message passing based graph neural networks, it would take as many steps as hops in order to get that information to the center node or the target node. And during that process, it can lead to information loss. There's much research surrounding it, which is over squashing and information bottleneck of sorts. But if we were to allow some global or rewiring mechanism, which enables attention to the distant nodes, it would alleviate the issues. So in order to get this, we can consider the key insight for building graph transformer is to have both local and global attention that enhances graph transformers. And this is a one insight that has been followed in most of the recent works surrounding modern graph transformers. So to conclude my introduction of graph transformers, I'll go through how to build a graph transformer. What are the key ingredients, and these are the mechanisms, or these are the aspects you can find in most of the recent works that come on building powerful graph transformer. The first is attention mechanism. We take advantage of using the attention mechanism to allow each node to attend to any other node features. There's some considerations are surrounding rewiring or surrounding what percentage of global or local attention to use. But overall, the first focus is on the attention mechanism. The second focus is on positional encoding or structural encoding. And the goal is to have a function which is defined on the graph structure that can inform the nodes about very important or meaningful information that the node has in the original graph, or kind of have positions of the nodes in the original graph. And the third is a way to have both local and global representations, similar to what I mentioned about the coverage of attention in the previous slide. So usually these days, graph transformers have both local modules and global modules, which have local level attention and some global level attention. And these representations are used to have a node build its final feature representations. Thank you so much. I will conclude here and pass to Rishi.
Hello all, my name is Rishi Puri, and I work at NVIDIA leading engineering efforts for PyTorch Geometric and research efforts for combining graph modeling and language modeling. PyTorch Geometric, or PyG, is a library for graph-based machine learning. It packages together state-of-the-art models and datasets with high-quality, easy-to-understand examples and tutorials. It is based on PyTorch and follows very similar usage patterns. NVIDIA provides a Docker container for effortless setup with the latest and greatest from NVIDIA and PyG. PyG is also fully scalable up to even trillions of edges with NVIDIA cuGraph. PyG graph transformers are very similar to other GNNs and require little to no changes to integrate into your existing workflows. Traditionally, graph transformers have been used for graph classification tasks such as molecular property prediction. PyG has a beginner's tutorial that covers training a graph GPS transformer on the zinc chemical design dataset. The task is to regress numerical chemical properties. This abstract diagram depicts how you can use PyG graph transformers. The first step is to initialize your dataset from torchgeometric.datasets. The next step is to inject your positional encoding. This is generally done with torchgeometric.transformers, which can be passed to PyG datasets as a pre-transform. There are some exceptions. For example, the model SGFormer, which I will mention later, uses a message passing GNN to encode both positional and local neighborhood information. The code snippet shown is an example of adding a random walk positional encoding as a pre-transform to the zinc dataset in PyG. Once you have your dataset, you would pass it to your data loader. PyG has three main types of data loaders, which all extend the basic PyTorch data loader. The one shown is the PyG data loader, which is generally used for predicting properties of graphs, such as molecular property prediction. This data loader randomly samples graphs from a list and then combines them into a single graph, with a vector that denotes which nodes belong to which graph. This may be needed for some PyG models. The neighbor loader is usually used for predicting properties of nodes in a graph. It is used to randomly sample a batch of seed nodes and then gather their multi-hop neighborhood, which gives a good random approximation of the graph's distribution. An example of my 2-hop social neighborhood is 5 random friends of mine and then 5 of their friends for each of them. The link neighbor loader functions similarly, but is used for predicting properties of existing edges in a graph or predicting the existence of new links. Once you've set up the previous steps, passing your graphs to any PyG graph transformer is similar to other PyTorch models, such as PyG's message passing GNNs. The code snippet shown is an example of how you could call a graph transformer. The Zinc dataset is a free database of compounds that you could buy online. The use is for doing virtual screening of potentially useful compounds before having to buy them. The machine learning task for the Zinc PyG dataset is to regress the numerical solubility metric of molecules in the database. This slide shows some examples of molecules in this dataset. I ran the existing PyG example code for Zinc and Graph GPS. Then I swapped in Graph Attention Transformer, or GAT, something that PyG makes trivial to do. I also tested Graph Sage. These are two of the most common traditional message passing GNNs. The results are quite impressive. Graph GPS is 4.3 times more accurate than GAT and 3.4 times more accurate than Graph Sage. Note that I used default hyperparameters in the example for Graph GPS, but I chose the best hyperparams over 6 trials each for the Sage and GAT models. We are now working on adding new graph transformers with examples for node and edge level tasks on large graphs. There are 4 new graph transformers coming soon, with the SGFormer model coming first. The Open Graph Benchmark node classification tasks are some of the most well-known and commonly used benchmarks for graph machine learning. The general task is to predict the properties of nodes in the graph. There are multiple challenges within this benchmark of increasing scale. The first is OGBN ArcSieve. This contains computer science papers indexed by the Microsoft Academic Graph, or MAG for short. This graph has 169,000 nodes and 1.2 million edges. Next is OGBN products. This is a graph of Amazon products with edges existing between items that were purchased together. This one has 2.5 million nodes and 62 million edges. Finally, there is OGBN Papers 100M. This one contains 111 million papers from the Microsoft Academic Graph, with about 1.6 billion edges between them. As we add each new graph transformer, we will integrate them into a shared example space. The first place of integration will be the node classification example for OGB node data. This is under example/OGBN train.py. The next place for integration is our example on how to accelerate the previous workflows using NVIDIA cuGraph. This is under example/OGBN train cugraph.py. Lastly, we will also integrate into our examples that show how to scale up such workflows. These are under examples/multi-GPU. As we add the rest of the graph transformers, we will choose the highest test accuracy one for the default in the examples, but allow users to choose between all of them using an arc parser. As some initial information on them, SGFormer is expected to be available next. This consists of a message passing GNN combined with global attention. Up next is likely to be polynormer. This model learns a polynomial function on top of local and global attention. The XFormer model is next. This uses local and global attention combined with sparse random walks. And finally, we hope to add token GT. This model is a very standard token transformer, but in order to tokenize our nodes and edges, we would use either Laplacian or random walk positional encodings. It also has a trainable parameter that indicates whether a token comes from a node or an edge. The same hyperparameters are used for each experiment. If you take a look at this graph, it's clear that SGFormer is better than the GraphSage and GAT baselines. If we look at the accuracies in comparison to GAT, we can see an increasing trend for SGFormer as we increase the size of the dataset. If we plot SGFormer minus the best of the two message passing baselines, and then plot this against the log of the number of nodes in each graph dataset, we can see a clear trend similar to what we see in language transformers. This makes sense since the baselines are message passing GNNs, and the SGFormer is just a message passing GNN combined with attention. We know that attention scales for language. Now we can see it might scale for graphs as well. This is exciting since cuGraph enables scaling to billions of nodes and trillions of edges, which represents the scale of many large organizations. It is still too early to be sure, but as future work, I will investigate this scaling across all new graph transformer models and include more datasets besides OGB in the future benchmark. To close off my section, I wanted to look to the future. My main focus over the last year has been combining graph modeling and language modeling to enable the next generation of AI systems. Last fall, I gave a lecture on my work at Uray's CS224W Stanford GNN class. See the QR code for slides. As PyG graph transformers mature, I will use them in my work to explore how they improve GNN plus LLM systems as compared to traditional message passing GNNs. This is exciting since graph transformers and language transformers both seem to exhibit scaling laws, which may combine together to make ever stronger AI solutions. We will also have a webinar later this year that will cover the latest in GNN plus LLM and then showcase this technology as an integration with Kumo's product offerings. Stay tuned. Now, Matthias will take it from here.
Thank you, Rishi. Happy to take over. My name is Matthias Fey. I'm a founding engineer at Kumo, and I'm very, very happy to share today how Kumo leverages graph transformers to build state-of-the-art models. And so Kumo AI is a relational AI platform that can handle diverse use cases such as personalization in the form of recommendation, customer retention, customer acquisition, entity resolution, fraud detection, forecasting, and many, many more. And so what all these use cases have in common is that they're basically operating on business data. And that business data usually comes in the form of a relational database. So in this figure here on the right, you will see that we have an example of a relational database that contains users and products, and then these users and products are connected through like orders tables of use tables. And so the blueprint of what we call now relational deep learning is that we can understand this relational database as an graph, as a relational entity graph, which is also heterogeneous. So it contains users and products, but it also contains all these fact information, which are also inherently temporal. And now the idea is that we can leverage graph machine learning and graph transformers in particular to make predictions for certain entities in our database. So you can select one of these users here, for example, and predict customer retention or give them recommendations for a specific article and so on. So we are using now graph transformers, shifting a bit away from message passing GNNs. And the way we do that is based on the key observation that we can understand a subgraph that we sampled around a user, that this subgraph, which is used as a computation tree in a GNN, can also be understood as a tree that we can sequentialize without loss of information. So you would see that we have a user here, and this user receives information from its surrounding neighborhoods to make an accurate prediction. And so now we can take all these nodes in our subgraph and actually sequentialize them or put them into a set of tokens. And that's what exactly graph transformers are doing. So what we're doing here is kind of like bridging the gap between what a message passing GNN does, is like getting this collaborative signal in, and also following the lines of work of like sequential recommendation, which sequentialize past interactions. And so what we are getting here is now a set of tokens that captures both past interactions and collaborative signal in the form of sampling across different hops and then applying multi-head attention on top of these tokens. The key to make graph transformer work is, as we have learned, is to add positional encodings that kind of preserve the graph structure or the heterogeneous information. But in our case, since we want to scale to supermassive large graphs, Laplacian or random walk-based encodings are too expensive for us to pre-compute. And so what we can do is we take in this multimodal heterogeneous input features that we have added here as a set of tokens, and we can add positional encodings to it. And so one positional encoding we can think of is the table type. So we can add information of whether this token refers to a user, a view, an order, or a product. Then secondly, we add the hop information. That means at which hop this specific node was sampled on. And that gives us an understanding of how far away or how deep in the subgraph this token appears. And then the two most important encodings here that we add are the temporal encoding, and we add these for all the fact tables. So all the facts in our database, part of a user-centric subgraph, actually contain temporal information. So their create date or when they have been placed. And we can use that to give the transformer basically an understanding of how the order of facts appear as we go through time. And lastly, to preserve like this subgraph structure, we add a tree encoding here, and that is used to preserve like child, parent, and sibling relationships. So we can now attend to a parent node, we can attend to a child node. So for example, an article can actually see like which transaction it was caused by. But we can also relate to siblings, like what are similar products a user bought, and they can all attend to each other. The key insight here is that relational graph transformers can actually learn anything on a database that you can think of. So this tightening up of this structural bias that message passing GNNs come with, we can kind of loosen it, but achieve like a much more expressive graph transformer model here that can actually learn group bys across multiple columns, multiple tables, and multiple hops. So just to give you an illustration of that is that they can learn, for example, filtering. So they can easily attend to like the last facts of the last week. They can also learn correlations between facts and articles and so on. So we can learn about what articles were brought together or whether there exists some regular or repeated patterns, such as a user buys a specific article every beginning of the month. We can also learn about, for example, time between certain events and so on. So this is all something you can not naturally catch or capture with a message passing GNN. And then lastly, the most important part is that we can now learn this weighted aggregation given by the attention scores we assign to every token. So the most major important takeaway here is that we attend to all tokens in the set, and this kind of gives us a more expressive aggregation that we can learn here than with just using a message passing GNN. And so I want to give like a short demo on how this actually looks like in Kumo. You can now try Kumo for free starting from the Kumo 2.0 release. If you follow this QR code here, you can actually request a demo and have access to Kumo for 7 days straight. We also published some example notebooks to get you started in like no time, but it's probably easiest to just dive in right away and look at it right here in this call. So I prepared this Google Colab here, which you can also find in the example notebooks. And once you have an API key, then you can start using Kumo by just installing its SDK using pip install. And then after you install it, you can set up a Python script or Google Colab, import Kumo, connect it to your specific environment, and get started with relational AI and graph transformers. So to give you an example of how that looks like, we provided a utility function that basically creates you or gets you a graph from RelBench, which is like a new benchmark to do relational deep learning. And we load in the RelStack dataset here. And so this now gives you a graph definition of a real world relational database. You can print out this definition here. So you could see that this graph contains 7 tables, for example, users and posts, and these users have votes pointing to specific posts and so on. So these are the tables. And then what defines our edges are like foreign key and primary key relationships. So for example, you could see here that a user points to a specific vote table, and then a vote points to a specific post, and that's how users and posts are related to each other. You can also print out the definition of a specific table. So you can see, for example, that the post table here has a primary key called ID. It also has a creation date, which means like when did this post appear in time. And then there exists additional columns here, which basically hold the feature information or the foreign key information. So you could see that a post comes with a title, it comes with tags, it comes with bodies, but it also comes with these keys, which are often marked with the ID suffix here. So for example, it has a parent ID to a specific post, or it has a link to a user who created this post. Obviously, you can have full flexibility in this SDK here, so you can easily modify certain columns, and you can also modify their types, which basically means how these things are encoded downstream. So for example, it makes total sense to interpret a comment as a text rather than a categorical column, for example. And then once you have this graph definition ready, you're basically up and running to start model training using graph transformers with as many use cases as you want. So how we enable use cases in Kumo is through our predictive query language. And predictive query is basically used to generate training and prediction tables, but also gives the model an understanding of what the task looks like and so on. So the RelBench task we're looking here at is the user engagement task, which is basically formulated as predict if a user will make any votes, posts, or comments in the next 3 months. And that translates to a predictive query language that looks as follows. So we are predicting whether the count of votes in the next 3 months is greater than 0, or the number of posts is in the next 3 months is greater than 0, or the number of comments is in the next 3 months is greater than 0. And we want to do that for every user in our database. You can see that predictive query now infers this task type here as binary classification, which makes total sense. So we would expect probabilities at output or like true or false per user. We are now ready to start our training table job, and this training table basically acquires training labels from historical or past information. And this training table is then also used to pass to the model in combination with the graph. Importantly, Kumo lets you also intelligently suggest a model plan, which is basically the definition of how our models look like. And so we can start with a suggestion here, and then we can fully customize it based on our needs. We can retrain based on different model configurations and see how models behave and so on. So in the form of a graph transformer here, we could set the number of layers to 4 and the number of attention heads, for example, to 8. We can use this model plan here to initialize our trainer, and then following similar principles as in sklearn or in PyTorch Lightning, we just call trainer.fit, passing the train table to it and the graph. So now this gives you a training job, and you can basically schedule as many jobs as you want, and they're all orchestrated by the Kumo platform and chained together and so on. So that's pretty dope. But most importantly, you can also inspect progress of training directly in the UI. So if I follow this link here, I get, for example, to this specific training job. I trained it this morning. I finished it in around 1 hour. And you can see that it holds our query information here. It holds information about what the model plan looks like. You can also see that Kumo launched 2 experiments as part of our AutoML routine. So this is like a fast run here. Obviously, you can schedule as many experiments as you want to find the best hyperparameters. You can also explore metrics over time, over epochs, according to different metrics and so on. Most importantly, we also have like an evaluation tab, which tells you that Kumo have chosen like a temporal split here, according to different time ranges. And you can, for example, look at the holdout evaluation here. So you would see precision versus recall curves, RC curves, and so on. And then the last point I want to make is that Kumo also provides a fully fleshed out explanation or XAI view. And it's using like state-of-the-art graph machine learning explainers here on top. So you can, for example, for a specific category and a specific entity, you can explore a subgraph. You would see that this subgraph here is pretty shallow. You can see which of these columns and entities are the most important that have been found by the explainer. And then you could also have like so this is like an entity level XAI view, and then you also have like a global graph level view. So here you would see that what Kumo thinks are the most important columns globally in your data. So for example, you can follow this creation date here of a comment, and that would mean that the more recent a user has made a comment, then the more likely it is, or the more likely the user is to also make a comment in the future, which totally resonates with our intuition of how our model of the signal our model should pick up here. If you have trained a model, you can also get like the test metrics from the Kumo SDK. So you can see that on the AORC it performs quite well. And you can also inspect like predictions and probabilities for specific entities here in your holdout data set. Once you have a model trained, you can now make predictions. So you can, for example, start a new session, load in your predictive query and your trainer, and you can run batch prediction here on as many entities and as many timestamps and future predictions as you like, which then gives you basically capability to query the future giving Kumo. That's all from my end. Happy to take any questions, but first, back to you, Katie.
Thank you, Matthias, and thank you, Vijay, also, and Rishi, for sharing your knowledge and practical examples. Now we'll begin answering question. For any question we don't have time to address, we'll follow up via email. So please use the Q&A section, because I'm receiving question in chat, but in that way our speakers are not able to see those questions. So that's why I want to ask you to use the Q&A section. That will ensure that our speakers can easily see and respond. Now I invite Vijay to start by answering 2 questions live, followed by Rishi and Matthias. So I hope, Vijay, you are ready. Over to you.
Yeah, thanks, Katie, and thanks everyone for staying throughout the webinar today. So there are a couple of interesting questions I can maybe answer live. There were other questions me and Rishi, we also tried to answer on the chat as well, so you can refer to them. But yeah, there's one important interesting question regarding um, the neighborhood node concept, as well as the context window that we see in the LLMs, for example. This question is by Abdullahi Al Mustafa, and the question I read is: how is the neighbor node concept connected to the context window in embedding? So we can imagine the nearest the node neighborhood for a node in graphs similar to the local context or the context window in LLMs. In graphs, when we say distant nodes, usually it would mean increasing the context length or context window. You can imagine, let's say a document has 1,000 words and our context window is just 100. For example, in a language model, it would be similar to a graph having 1,000 nodes, and the nearest neighbors, or maybe one hop neighbor, has just around 100 nodes. So the concept of having distant nodes in graph setting is similar to having possibility of having all connections to all tokens in the case of text. So usually when we see the long context model these days in LLMs, that is similar to having a truly global attention or some sort of approachable global attention in graphs. I hope that touches on the answer to extent. There's another interesting question which was about direction, like the question is from Alexander, and the question reads: as I remember, there is some difficulty if we are dealing with directed or indirected graphs. Can the application handle both? The answer is just the Laplacian operator cannot handle directionality, and we have to include some sort of some operator which can be directional aware. And there's an interesting work on this from DeepMind last year, which is titled Transformers from Directed Graphs. I can share the link later, but the core concept is Laplacian is is isotropic operator, like it doesn't have a direction sense. So we have to define operators which can encode directions, and in that work they for both the random walk based encodings and the Laplacian encodings, they first try to define the operator which is directional aware, and they have some inspiration from physics which can be used. For example, they have a magnetic Laplacian operator that can be used to have the direction sense as well as directional aware random walk. So when we replace those operators and perform the usual operations, it's a way to have positional encoding with directed graphs, for example. So the answer is if we're using the straightforward Laplacian operator, it cannot. But yeah, there are methods that can be used to design positional encodings for direction-aware graphs as well. Yeah, maybe I'll pass to Rishi for some questions that he can take.
Yeah, totally. I saw a good one. I'm scrolling back to it. Sorry. Yeah, so from Fahad, question to the previous speaker: do you have any resources on graph to sequence models for predicting sequences from graphs, specifically models that take in a graph as input and generate a path within the graph, such as predicting the shortest path? So I don't have anything specifically for that, like very specific use case, But as I mentioned before, I work on GNNs plus LLMs. And so the goal there is essentially to take in graph-based data and output sequential data, such as language. And this is highly multimodal, and it works in like biology settings. So there are cases such as protein MPNN, which if you've heard of AlphaFold, takes in a sequence of biology stuff and creates a shape from it. Protein MPNN is kind of the opposite. It takes in a shape and outputs the biological sequence. And so there are already examples in PyG for very similar use cases. Protein MPNN is coming in the next hopefully month or two. But yeah, there are examples like molecule GPT where you take in a molecule and you predict like language about it, such as, what would the solubility of CO235, whatever. Yeah, something like that. So definitely this is possible today with what is in PyG. And I would say just reach out to me if you have specific, data sets or specific use cases you want to look at. Yeah. Other than that, I saw one from Yuri about over squashing. I think maybe BJ could talk a little bit more about it, but the basic issue is they said, okay, we've seen GNNs have issues with over squashing, and they asked, does graph attention solve this? Yeah, the global attention of graph attention should address these issues. Yeah, maybe Vijay could talk a little bit more about it if he wants to. But yeah, I think that should address the issues. And I've clicked the answer live button, so those should be addressed.
Okay, I have one question that asks, how does Kumo compare to any open source alternative? And I think that's a great question. I think the main goal of Kumo is to make graph machine learning and graph transformers accessible without you needed to have a PhD to make fully use of it. So I think there exists great open source solutions out there, such as PyG, obviously. You also have the Relbench repository, which kind of has this blueprint implemented to some extent with GNNs. The main advantage if you want to use Kumo is that this is obviously a fully SaaS product that can operate in a cloud environment and where you can orchestrate jobs and have like a fully production ready system up and running with stability ensured. And it also comes with a scalability in mind. So you can basically, Kumo basically supports any graph size of any scale, and you can expect that Kumo finds the best hyperparameters and models in least amount of time possible. And then obviously, besides just model training, you get all the benefits, like you get statistics evaluation, you get batch prediction support, you get explainability, and so on. So I think there exist open source alternatives to dive into relational deep learning. If you really think about productionizing a use case and so on, then I think Kumo is like a super good fit. There's another question that asked how Kumo supports connectivity to diverse databases and so on. Examples would be great. Does Kumo partner with startups to launch proof use cases rapidly? So Kumo can connect to a variety of databases and cloud data warehouse and so on. So we have like native support to Snowflake, native support to Databricks. You can bring your own connector, and you can bring in Parquet files and so on. And we're constantly working on improving our connectivity to other database types. You should be able to find full examples of that in our documentation, and you can reach out to mail if you're unable to find that. I'm happy to send them to you. We're also working with partners and so on to improve our models, explore new use cases. So if you have something interesting in mind, happy to set up like a proof of concept. Vijay, anything on your end?
Yeah, I wanted to touch on the issue of oversquashing, right? So there was one slide that I shared like during my presentation, which talked about like the coverage of attention and how it can help with oversquashing. So what happens generally in graph neural networks is when we have messages coming from distant nodes, the neighborhood going from 1 hop to 2 hop to 3 hop and so on rises exponentially. So if there are many nodes sending information to one center node, and it's coming from exponential blow up of neighborhood from different hop, there's a potential of information getting over squashed because all of them want to get to just one vector reaching towards the distant. So what global attention would do is it would have a direct connection to a distant node instead of traversing the information from a distant node in k hops, which where k is the distance to the node from the center. So there's a very nice investigation from this by a paper which is like on the information bottleneck and over squashing in GNS. The paper title is something around this. So in a sense, what Rishi said, that's like the graph transformers with global attention can be a way to alleviate the bottlenecks, and even in the paper that investigates the bottleneck and over squashing, there's a quick remedy that they do if they connect provide a fully connected graph for one layer towards the end of a graph network. That's also one way to alleviate the issue. But the gist of having over squashing and trying to alleviate is that there are distant nodes. The information is difficult to reach. There are certain cases of information which is difficult to reach to a center node, and then if we were to extend the coverage of, let's say, message passing, or for the same case, attention, it would be a way to alleviate it. Yeah. And touching on some other questions, give me a moment. I think there was one regarding weights. I think, yeah, edge. How can graph transformers be used with text and maybe some information on the edges? So there are like hybrid combinations of GNS, for example, Graph GPS or XFormer, something which Rishi shared as well. So there are these methods where a hybrid graph neural network plus transformers are used. Transformers provide attention both in the local and global perspective, and then graph neural networks can be used, which can be used to incorporate edge features. So in such a hybrid sense, edges can be used, which will be towards an edge defined message passing network, or maybe the transformers which also build on the edge, similar to edge conf, for example. I think that the quick answer to this is yes, there are ways to incorporate edge information in transformers, or maybe hybrid GNN plus transformers. And the following question was, how can it be used with text? So I think the resources shared by Rishi is the great, I think the best point for looking at this, because LLM plus GNNs, there are many interesting work being done there, and I think the way the questions of how graph informations can be used as in context prompts for LLMs, how can graph information be retrieved and used an embedding for an LLM input. So there are these directions, and I'm sure Rishi has. I mean, Rishi, the links that you shared, they are very good starting points for these things.
Yeah, and so following up on that, I saw one question that wasn't in the Q&A, but I thought it was relevant. We've already answered it in the webinar chat, but someone mentioned first that Kumo can handle structured data, but Greg answered that. But for the part about unstructured data, I mentioned that this was an issue we faced in GNN plus LLM. What if you don't have a graph? And so to solve that, which many customers don't have graphs, we created a text to knowledge graph system. I'll go into it much deeper in our future webinar, but it's in the slide deck, and I screenshotted the relevant slides. So yeah, take a look at that. And then to answer some of the actual ones from the Q&A, I see from Canberk Ozen, I arrived late, but wanted to ask if MPNN is worth using for modeling graph. Basically, they mentioned they have long-range interactions in graph, which is an area where MPNNs fail. They ask, are there any other disadvantages to graph transformers besides their computational load? And they've heard that they may have more issues modeling the locality of nodes as compared to MPNNs, while MPNNs fail with over squashing. So as you know, Vijay already mentioned the over squashing part, but I wanted to make sure that it's clear that graph transformers shouldn't have issues with locality, since we're not just talking about global attention when we say a graph transformer. Global attention is just a piece of it. They like you know, Vijay has showed, and I mentioned for all those other transformers, we also still need a local embedding and the positional embeddings. And so this is handled sometimes under the hood. For example, like with SGFormer, it's actually using a message passing GNN, right? So if you're using a message passing GNN plus global attention, you know, you're basically getting the best of both worlds. And then all the other graph transformers are basically capturing similar information in alternate methods. And so other than that, I saw one from Ashwin that said, I'm interested in the applications of GNNs to chemical structure analysis and nanomaterials. Do you have examples where GNNs represent molecular connections that are mapped through transformers? So that's basically the graph GPS example that's in the slides. Yeah, it's basically predicting solubility of something, but you can predict any property if you have the data for that labeled by professionals. Yeah, I'll hand it off to Matthias.
Okay, yeah, I have one interesting question about are Kumo ML tools mostly for static graphs, or could you run transductive inference on new nodes and edges? I think that's a very interesting question, and I want to point out that our graph transformers in Kumo are all designed for temporal graphs, so you take temporal information into account. And that also means that you can apply it on unseen nodes and unseen edges during inference. So you can train your model at a specific point in time, but then run predictions as long as you want on updated nodes and edges. And that also holds for recommendations. So you can train your specific model, but then recommend items, for example, that were never seen in the training set, which is like a super cool property of GNNs in general and graph transformers in specific. The other question I want to answer is about handling of multimodal data like images and videos. Specifically, which modality-specific encoders do you recommend, and how are their features integrated with the relational data in the graph? So I think that's a really interesting question because our goal is to support any kind of data. So you can think of categorical data, multi-categorical data, and so on. And these are all kind of like standard routines, how to encode them, and so on. And it gets more interesting once you move to images, videos, text, and so on, because now you have a variety of ideas of how you can actually integrate them into the model. And so the first thing, like the most general, obvious way is to just use like an external model and compute an embedding for each of these, which you can now input into the graph transformer. And I think this is like the most general approach because it gives you the best amount of flexibility on how things should be encoded. And then for Kumo in particular, we provide all encoders for these kinds of stuff. So for example, we have our own text encoders, which are trained end-to-end in combination with the graph transformer. We have our own image encoders. And then we also have access or a feature where you can get an embedding from an LLM. And if you follow like GNN literature and research, then text attributed graphs are like a super hot topic. And in general, it says that the more powerful your language model is, the better the embeddings are for a specific downstream task in a GNN. So having like access to OpenAI or other vendors gives you like the best embeddings for your specific task here. Vijay, anything on your end?
Yeah, so there was one follow-up to the directionality in like directional position encoding. So right, so I've shared the link on chat for the paper, which is Transformers Meet Directed Graphs. So if I saw there's multiple interest on that topic, so it's a good starting point. But I think the core concept is if we are trying to define an operator on graphs, which currently doesn't handle directions. We have to modify the core of it, and then even if it's for random walk or for Laplacian operator, if we can find a way to make it directional aware and then get information out of it, that's the approach, and that the paper that I shared is a good starting point. There are also other questions on what can be what graph transform model. This question is from Sokolov. I'm sorry for the pronunciation, but yeah, the question is, what graph transformer model would you recommend for molecular representation tasks to produce embeddings? I'm trying to benchmark a series of molecular foundation models for cancer drug discovery, so I'd share the suggestion. So yeah, for the molecular tasks, if let's say the data sets are just defined by graphs without any three-dimensional information, they where additional invariances are not to be modeled, graph GPS is a good starting point. There has been further developments of it by some of our collaborators, which is like GPS plus and mole GPS. So for molecular task, I would recommend having a start from graph GPS, and there are also further developments on it. For example, XFormer and SpexFormer from a group, another group as well. So the overall core is the global attention usually in smaller molecular graphs can be very feasible. So we can simply plug in a global transformer. And for MPNS, any edge-based message passing-based CNN. So these two kind of construct the learnable parameter layers of the graph GPS, and there are positional encodings and structure encodings which try to incorporate the chemical structure of coming from the molecules. So if you refer to GPS and GPS++, after speaking, maybe I can drop a link to these papers as well, although they were in the slides. But yeah, that is the recommendation I would say for molecular tasks, because usually for molecular tasks, if the data sets are just defined by the graphs, we can simply use graph GPS. If there are other aspects, if the 3D information, if you want to tackle about rotational, translational invariances, then there's another line of work in geometric deep learning and graph learning literature in general that can tackle those as well. But if we were to build a graph GPS, kind of extend graph GPS to handle those properties, we will have to extend the principles that were used by those papers to have a GNN that respects translation and rotation symmetries for three-dimensional molecules. So the answer depends on whether your data is two-dimensionally defined, is just defined by the graph structure without any three-dimensional property that you are modeling. Or if it's three-dimensional, then there's another direction that you can follow. I'll try to put the links here. If not, if I miss somehow, then you can follow me for later for more detail on this direction. Yeah, and there's I think there were two questions on the molecular, so I hope it answers that. There's also another question on the ability to help with subgraph isomorphism or matching problems. The relationality aware graph encoding seems like they could help with path optimization problems. So I think there are multiple problems mentioned in this question, but if I were to touch the subgraph isomorphism, there are some interesting line of work that tries to create subgraph GNNs. In a way, if we look about what kind of information positional encodings provide, it allows both graph neural networks as well as transformers to have additional information beyond what a very basic message passing based GNNs can capture. And there's a great amount of theoretical work on that, where GNNs are compared with Weisfeller-Lehmann hierarchy of algorithms for detecting non-isomorphic graphs. So if you go on that direction, there are like conclusions or equivalences where message passing neural networks have certain limitations, and these are solved by positional encodings. So if we have subgraph based GNNs, that's also a way to break the symmetry and provide the graph neural network or the graph transform with certain information. Whether it solves the subgraph isomorphism problem or not would be similar to I think the answer to this would be similar to extending the graph isomorphism thing and applying it on a subgraph, which is similar to the investigation that is done in the line of subgraph GNN's work. I can share a link to this as well. Let me mark for this as well. Yeah, there's another question on, we spoke about, this is by Atul. We spoke about how Laplacians can't encode directionality. What about random walk? So I think, yeah, the same principles applies. If we are to bias or change the random walks to directionality or make it directional aware, then that's a way to go. It's in the same link that I shared, the paper called Transformers Mean Directed Graphs. You can read more in detail about it. Yeah, maybe one more question I can touch. Can graph transformer be efficiently integrated into RL pipelines for decision making in structured environments? I think I haven't seen any concrete work on this direction, but conceptually I would say it can be. The problems or the challenges on this would be the complexity of the graph that we would see in, if let's say we are defining such environments, or whether we can have a precise definition of how to define different objects in structured environments. What's the finite set? How direct interactions are defined. So if we were to come up with some definitions on that, I think conceptually it's possible. It's maybe the challenges would be the data sets, the complexity of like how the graph sizes fare in these environments and so on. But conceptually, I think it should be possible, because why we use graph neural network or graph transformers is to have a model that can learn from rich interactions which data objects process, or maybe different nodes process. Yeah, maybe Rishi, if you have any other.
Yeah, totally. I just wanted to follow up on the last part that Vijay mentioned. I'm not sure if I fully understood the question, but in case this helps further answer it, I like, today a lot of models do like reasoning and like that's the new thing, right? Reinforcement learning and reasoning. And this creates a graph. And that is a future direction of work, for NVIDIA and my team. So we are combining graph neural networks and transformers with reasoning models in the future, but definitely further out. So yeah, stay tuned. For questions that I saw on the list, Bikram Adhikari asked, I may conclude there are no scientific computing use cases for Kumo or GNNs. I would say it's like that's very like it's the exact opposite, basically. PyG has a lot of examples for science. I just mentioned the molecule GPT example, where you can basically just talk to a molecule. And there's many more examples, and it'll keep getting added. Kumo can also do these things if you have tables of science. And NVIDIA has specific things for science, such as modulus, which is like physics-based simulation using GNNs. So this can be done for fluid dynamic simulations. We use it for controlling the hot gases in fusion reactions. Yeah, pretty much weather, like anything that's grounded by physics, which is science. You can use GNNs to model it better and more efficiently than traditional calculus differential equation based approaches. And then the other one I wanted to answer is, are you seeing, sorry, could you speak to examples and promise success you are seeing in terms of applying GNNs to design exploration, where GNNs plus LLMs would show great promise? Basically mechanical design data that combines geometry with unstructured metadata. We don't have examples of this today, but please reach out if you want to share data. I can help, or even if you don't want to share data, I can still help make that happen. But yeah, in general, any use case of combining unstructured and structured data, like graphs and language or graphs and images or whatever, it's possible with what exists in PyG today. Maybe minor modifications needed, but yeah, just reach out to me for anyone watching, and yeah, always trying to expand the amount of use cases that this hits. Matthias?
Yes, I have one question on spatial temporal graph data. So fixed graph nodes created by spatial distances, and how graph transformers and Kumo supports these. So I think that's a really cool question. I think we talked about temporal graphs at Kumo quite a lot, but not necessarily spatial temporal graphs. And so I think the cool thing about graph transformers and spatial temporal graphs is that you basically get your positional encoding for free here. And so you can use the spatial distances as absolute positional embedding or encoding if you have one. You can also encode it relatively. And so graph transformers are like the optimal choice here for these kinds of tasks, in my opinion, and much easier actually to integrate than via a message passing GNN that needs to go through edge features and so on. So graph transformers basically support that out of the box. In Kumo, you can also do that by just adding these positional encodings that you have, or these spatial distances, as features or columns in your relational database. Another question I have is on multitask learning and graph transformers and how can they be combined. I think that's a very interesting question as well. Haven't talked about multitask learning here yet either, but I think especially if you look at GNN works and machine learning work in general, then you can see that multitask learning especially helps on tasks where you have like sparse labels and so on. You can also use multitask learning as some form of pre-training, and we see that multitask learning actually helps to learn better representations using GNNs or graph transformers. The way you can combine these is pretty straightforward and in general follows the standard paradigm of how you do multitask learning in any machine learning pipeline. So the graph transformer is just responsible for getting you a representation, but how this representation is then used downstream in an end-to-end fashion is basically up to you. And obviously you can do a multitask learning approach here on top of the representations, independent of whether you're using graph transformer or any other deep learning model.
Thank you. So we've reached the end of our workshop. Thank you all for joining, and thank you for your amazing question and positive comments as well. I hope you've gained valuable insights. Tomorrow, as I mentioned in the chat, we will send you an email with the video recording, example notebooks, and free trial links. And thank you once again for your time and attention, and have a great day. Thank you also, Matthias, Rishi, and Vijay.
Thank you.